All right, welcome. The ocean floor is one of the last truly unexplored frontiers on our planet, and it's hiding these vast resources, things like oil and gas. But finding them? That's a whole other story. Today, we're going to dive into some absolutely fascinating research that asks a pretty huge question. Can we actually teach an AI to be a kind of digital geologist, to map these hidden treasures miles beneath the waves?
I mean, that really is the heart of the problem, isn't it? You can't just send a submarine down with a camera. We're talking about mapping solid rock, thousands of feet under the seabed. So, how in the world have we been doing it up until now? Well, it turns out it involves making a whole lot of noise. Okay, so before we get to the really cool AI stuff, you gotta understand the old school method. It's called seismic mapping. And it's ingenious, but it is incredibly difficult. Think about it like this. Imagine trying to figure out the floor plan of a skyscraper by standing outside and just shouting at it, and then trying to build a map based on the echoes you hear back. That's kind of what we're talking about.
Yeah, it's basically a giant ultrasound for the Earth. It's kind of like a three-step dance. First, you create a really powerful sound wave. Second, you listen, very, very carefully, as those waves travel down, bounce off all the different layers of rock, and then come back up to your sensors. See, every single echo carries little clues about what it hit. And then third, you take all that jumbled echo data and try to piece it together into a picture that makes sense. And here's the catch. Turning those echoes into a useful map is what scientists call an ill-posed inverse problem. Now, that's a really technical way of saying it's a massive, chaotic puzzle. There are a huge number of possible right answers, and just a tiny bit of noise in your data can send you way off track. Solving it takes an unbelievable amount of computer power, which, as you can imagine, costs a ton of time and money. And this is where our story takes a really interesting turn. So, enter the hero of our story, artificial intelligence. Researchers started thinking, okay, what if instead of trying to brute force the math, we could train an AI to develop an intuition for this, to just look at all that raw echo data and see the map? The way a human geologist might, but, thousands of times faster. To pull this off, they use something called an artificial neural network, or an ANN. Now, this is a system that's literally modeled on our own brains. It's made of all these digital neurons that learn by just looking at tons and tons of examples, spotting patterns, and then adjusting their connections. It's not about programming a bunch of rules, it's about letting the machine actually learn for itself. And the specific kind of ANN they used is called a UNet. And this is where it gets really interesting, because UNet has a very special talent. See, most AI you hear about are classifiers. You show them a picture and they tell you that's a cat, or that's a dog. UNet is totally different. It's a generator. It learns how to create brand new images. And this slide right here shows you the whole ballgame. A standard AI takes in an image and spits out a simple label. Cat, dog, done. But UNet, it takes in data, in this case, all those messy seismic echoes, and its output is a brand new, complex image, the geological map itself. It's not just identifying things, it's creating them. And that is the absolute key that makes it so perfect for this job. So the researchers had their tool, but now they had to train it. I mean, how do you teach an AI to become a geologist? Well, you give it a textbook, and then you give it a test. A digital one, of course. So here's how they set it all up. They basically had two AI students, the standard UNet and a slightly tweaked version they called UNet Mod. Their textbook was a huge data set of simulated seismic data where they already knew what the correct map was supposed to look like. The AI's job was simple. Look at the seismic data and draw the map. Then, the researchers would compare the AI's drawing to the real answer to grade it, testing it on everything from easy, simple layers to really complex stuff with faults and folds. So, after all that training, how'd they do? Did our AI students pass their geology final? Well, their results were genuinely impressive, but they also came with this very strange, very fascinating little quirk. The headline number you need to know is a big one, 75%. On average, the maps the AI generated were about 75% similar to the actual real maps. Now, they measured this with a tool called the Sorensen-Dice coefficient. Just think of it as a score for how well two shapes overlap. Getting a B, a 75% on a problem this complicated on your first try, that's a fantastic result, and it proves this idea has some serious potential. And if you break it down a bit further, you can see how it handled different problems. For the simple geological models, boom, it nailed it, incredibly accurate. When things got more complicated, with all those folds and faults in the rock, it still did a really good job of getting the big picture right, even if some of the finer details got a little blurry. Still, an amazing performance. But then, something weird started to happen.
The modified version of the AI unit mod, it started seeing things. As the research paper puts it, it began producing a circular artifact in the top right corner of its maps. The researchers think the network basically just learned a bad habit. It saw faults in that same region so many times in its training data that it started to overgeneralize. It just started drawing one in every single time, even when one wasn't really there.
But here is where it gets really, really interesting. Despite this strange little quirk, the data showed that the modified AI, the one that was seeing things, was actually more stable. Its performance from one test to the next was way more consistent. The standard UNet had higher highs, but also lower lows. UNet Mod, on the other hand, was reliably consistent right around that 75% mark. And this leads to a really fascinating question for developers, right? What's more valuable? An AI that's a little unpredictable but just might, give you a perfect result? Or one that is reliably good but has a known consistent flaw you have to account for? I mean, for an oil company, that's a multi-million-dollar question. Do you pick the stable model, knowing you have to manually fix its little mistake every time? Or do you roll the dice on the other one, hoping for a masterpiece but risking a total failure that could cost you a fortune? Yeah, there is no easy answer to that.
Okay, so let's zoom out and try to put all of this together. What are the big takeaways from this whole exploration into AI-powered geology?
So what's the bottom line here? Well, first, the promise is huge. AI can clearly make this incredibly slow and expensive process way, way faster. But second, the reality is it's not perfect. Not yet. It still struggles with the really complex stuff, and it can develop these weird habits. And that leads to the third point. The next step is pretty clear. The AI needs a bigger, better textbook. Not just more data, but more diverse data, showing it all the weird, messy, exceptional geology that'll help it break those bad habits and really learn how complex the Earth is. And that's really what makes this so exciting. You know, this isn't just about finding oil. This is a proof of concept. It shows that we can train an AI to look at incredibly complex, noisy data and create a clear picture of a world we can't see. And that just leaves us with this final thought. If we can teach a machine to see through solid rock, what's next? Mapping the unbelievable pathways of the human brain? Visualizing the invisible forces of dark matter? The possibilities, well, they're as deep and as unexplored as the ocean floor itself.